lecture on linear algebra for machine learning. So in today's lecture, we will review the important linear algebra concepts crucial for understanding the inner workings of important machine learning algorithms. We will talk about vectors, matrices, determinants, and other mathematical objects, together with their properties and operations. So we will cover the following: vector properties, matrix properties. We will also talk about determinants and their properties. Then we will discuss the Gram-Schmidt or orthogonalization procedure. We'll talk about positive semi-definiteness and its importance, eigendecomposition of square matrices, singular value decomposition of a general rectangular matrix, and we will conclude today's lecture with a brief discussion on the fundamental theorem of linear algebra. Let's start by asking the most basic question. What is a vector? A vector is a mathematical object that has elements arranged in a list or in an array. So in this lecture, we will restrict ourselves only to elements that are real numbers. In the future lectures, we will relax this restriction and consider functions, derivatives of functions, and other mathematical objects as elements of our vector. So vectors reside in vector space, which we denote by uppercase V. There are two operations that are defined for vector space: vector addition and scalar multiplication. Vectors may be added together and multiplied or scaled by scalar numbers. Vectors are closed under addition. This means that two vectors in the vector space V, when added together, will result in another vector that is also in V. Vectors are also closed under scalar multiplication. Since a vector multiplied by a scalar produces another vector that resides in the same vector space. Vector addition and multiplication obey the commutative, associative, and distributive properties similar to the more familiar real numbers. Let's go through these properties one by one. Commutativity for addition means that the order two vectors are added does not matter. The sum will be the same. Associativity means that the sum of three vectors remains the same regardless of how the vectors are grouped. The third is existence of the additive identity. This tells us that there is a zero vector which has zero magnitude and no direction, and this zero vector, when added to any vector, will not change that vector. Then we have the existence of an additive inverse. This means that for any vector, there is another vector that, when added to the first, will produce a zero vector. Multiplicative identity. This property means that multiplying a vector by 1 leaves it unchanged. Distributivity of multiplication. This means that for two vectors Sorry, this means that for two scalars and a vector, the order by which you multiply them does not matter. Distributivity of multiplication over addition. This means that given two vectors and a scalar, the product of the sum of the two vectors is the sum of the products of the scalar, and the individual vectors. And similarly, given two scalars and a vector, the product of the sum of the two scalars and the vector is equal to the sum of the products of the vector and individual scalars. Let's define some terms. Linear combination. A linear combination of a set of vectors S, whose elements are x1, x2 up to xn, and the vector space V is a vector of the form a1 x1 plus a2 x2 plus up to an xn, where a1, a2 up to an are real numbers. If the coefficients ai are positive and their sum is 1, we have a convex combination. Span. What is the span? The span is defined as follows. The span of a set of vectors S equals x1 up to xn is the set of all linear combinations of S. So we denote this by span x1 to xn, and it's this quantity here, such that a1 up to an are members of are real numbers. Linear independence. A set of vectors is said to be linearly dependent if there exists a set of coefficients a1 to an, at least one of them is non-zero, such that this condition is satisfied. A set of vectors is said to be linearly independent if this is satisfied, and the only way for it to be satisfied is for all the coefficients to be zero. Basis. A set of vectors x1 to xn is a basis for a vector space V if x1 to xn are independent and x1 to xn span the vector space. That means V is the span of x1 to xn. For example, we have this set of vectors. These vectors reside in Rn, and then there are n of these vectors. The first vector has 1 for its first entry, and the rest are 0. The second vector has 2 in its second position. Second element has a value of 1 in the second, see index 1, it's index 2. Then the rest are 0. And this should be 0, sorry. 0, 0, 0 up to the last one, which is technically the last one, 0. And the last entry will have a value of 1. So this set of vectors is called the standard basis of Rn. Rn, of course, has many other bases. So let's have other examples. 1, 2, and 3, 5. This set here is a basis of R2. Because these two vectors are linearly independent and they span the vector space R2. How about the second one, this one, 1, 2? Well, it's linearly independent. It's alone, so it's linearly independent. but it is not a basis of R2 because it is not span R2. The third one spans R2. Okay, it spans R2, but it is not a basis because this set is not linearly independent. So if you add the first two, okay, you come up with the third vector. So this vector here is not linearly independent of the two others. Subspace. Let V be a vector space and U be a subset of V. Then U is a subspace if the following are satisfied. You have additive identity, which means that the zero vector is in that subspace. Second, close under addition means that if vectors x and y are elements of U, then the sum x plus y is also in U. The third condition is closure under scalar multiplication. If A is a real number in R and X is an element of U, then the scalar product AX is also an element of U. And take note that the subspace U is a vector space in its own right, satisfying the properties of a true vector space. So with this definition, we see that the two-dimensional space R2 is not a subspace of R3, since their dimensionalities are not equal. On the other hand, the vector space defined by the set of vectors whose elements are real numbers A1, A2, and 0 is a subspace of R3. Then this 0 vector is the smallest subspace of V. V itself is the largest subspace of V. And finally, the empty set denoted by this symbol here, this curly bracket, or the symbol, is not a subspace of V, since a subspace is a vector space and therefore must contain at least one element, namely 0. So this condition must be satisfied. That's why this empty set is not a subspace. Definition of the inner product. The inner product of two vectors, x, y, is the product of the transpose of x by y. So this is something that's familiar. We have studied this previously. Just take note that when we do the inner product, the vectors must be arranged in this manner. It must be in this form, row by column. Okay, row by column. And the inner product is a scalar. The outer product, given two vectors x and y, the outer product, denoted this way, is obtained by multiplying each element of x by each element of y. The result of the outer product operation is this matrix. So the outer product produces a matrix. The inner product produces a scalar. The outer product is produced by multiplying a column vector by a row vector. So this is column by row. When you have column by row, you produce a matrix, not a scalar. Then take note also that the outer product is not commutative, meaning x cross y in general is not equal to y cross x. Vector norm. So this is one of the, this topic, this concept of vector norm is very important. It comes up a lot in machine learning, so it's important to study this well. So a vector norm is a function that maps a vector into a non-negative real number. It assigns a real valued length, which is, non-negative, of course, to each vector. A norm has the following properties. For all vectors x and y in the vector space V, and for any real number a, the norm of any vector x is non-negative, okay, non-negative, and the norm is 0 only if and only if x is 0. In other words, the only way for the norm to be 0 is the case when x is 0. So the norm of a non-zero vector is always positive. Then we have the triangle inequality. So the norm must obey this inequality. This means that the norm of the sum of vectors x and y is less than or equal to the sum of the norms of the two vectors. The third property tells us that scaling a norm of a vector scales the vector norm by the same amount. So these properties allow different notions of length. Okay, so the vector norm is not not uniquely. Well, then there are many types of vector norms. Okay. So there are many types of vector norms, and here are just a few of them. These are the ones that are commonly encountered in machine learning. The L1 norm, denoted by double bars with 1 as a subscript, is simply the sum of the absolute values of the elements of the vector. This L1 norm is also known as the Manhattan norm. The L2 norm, denoted this time by, again, double bars with 2 as subscript, is the Euclidean distance, which is the square root of the sum of squares of the elements of the vector. And this L2 norm captures the intuitive notion of distance as we know it. Then we come to the L infinity norm. The L infinity norm gives us the largest magnitude among the vector elements. So you scan to the values in the vector, the largest value, that's your L infinity norm. The weighted L2 norm is similar to the L2 norm here. For this weighted L2 norm, each coordinate of the vector space is given its own weight. And this norm returns the square root of the sum of the weighted squares of the vector elements. So all these norms appear in many applications in signal processing, computer vision, neural networks, and so on. Let's talk about the P norm. The P norm generalizes all the norms that we have talked about in the previous slide. So all these all the other norms, all the previous norms that we have discussed in the previous slide, the L1, L2, and L infinity norms are actually derivable from the P norm. So you just set P to 1, you have the L1 norm. P to 2, you have the L2 norm. And the L infinity is just P equal to infinity here. The unit ball. The unit ball is the set of all x in Rn such that the norm of x is 1. And the boundaries of the open balls for some P norms are shown here. So the L1 unit ball is diamond shaped in 2 dimensions. For L2, the unit ball is a unit circle in 2 dimensions. In n dimensions, the unit ball is a hypersphere. The L infinity unit ball is a square in 2 dimensions. Yes. And it is a hypercube in n dimensions. What about the weighted L2 unit ball? The weighted L2 unit ball is an n-dimensional hyperellipse. Okay, what about this? The case when P is equal to 1/2. Here, you observe that all the unit balls are convex. So meaning the internal of each unit ball here is convex, no? Okay, so that's what characterizes a true norm. But here, for P equals 1/2, this is not a convex. This is not convex. Therefore, when P is equal to 1/2, we don't have a true norm. So the most commonly encountered vector norm is the L2 or the Euclidean norm. It measures the length of a vector. It is equal to the inner product of the vector by itself. And we compute this norm by taking the square root of the scalar product of the vector by itself, the inner product. When the norm is equal to 1, we have a unit vector, and the vector is said to be normalized. However, when the vector is not the norm of the vector x is not 1, we can actually normalize the vector by dividing the vector by its length. And we do this by dividing each of the elements of the vector by its length, which is this. And this now results in a unit vector. Matrix norms. Vector norms measure the length of a vector. Vector norms measure the length of a vector. What about matrix norms? Matrix norms measure how much a matrix could possibly stretch a vector input. So we have this following definition. A function denoted by double bars mapping an m by n matrix of reals into a non-negative real number is a matrix norm if it satisfies the following properties: positivity, scaling, and the triangle inequality. There are two types of matrix norms: the element-wise or vector-based p-norm, and the norms, matrix norms induced by vector norms. The general formula for the p-norm of an element-wise matrix norm is this formula here. Here's the definition of the matrix induced norm. Given any vector norm, the induced matrix norm, okay, this one is the supremum of the norm of AX divided by the norm of X. And it's equal to this. So the supremum is the least upper bound. Let's now talk about element-wise or vector-based matrix norms. First, element-wise matrix norms are also called vector-based norms for this reason. For a given matrix A, we create a vector whose elements are the columns of A stacked on top of each other. So in other words, to create the element-wise matrix norm, we just stack the columns of the matrix on top of each other, and then we use the vector norms that we have learned previously. So for example, for p equals 1, we have here a matrix norm that is the absolute value of the sum of all the elements of the stack vector. Okay. Then the Frobenius norm is computed by taking the square root of the sum of squares of all the elements of the matrix. So in terms of the stack vector, this norm is the square root of the sum of squares of the elements of the vector. So it's also equal to the square root of the trace of A transpose A, and this formula here, which at this point may not be understandable because you don't know what the trace is. We'll define it later on. And this lambda here is your eigenvalue, which we'll discuss later. Sigma here is also to be discussed later. It's called the singular value. Now, the maximum norm is the largest element in the entire matrix or in the stack vector. We have the following induced matrix norms. The L1 matrix norm is the maximum of the L1 norm of a column of a matrix. To obtain this norm, we sum the absolute value for each column and take the largest sum. So it's also called the maximum absolute column sum matrix norm. The L infinity matrix norm, also called the maximum absolute row sum this time, is computed by taking the sum of the absolute values along each row and then taking the largest sum. So this L2 spectral norm is the largest singular value of the matrix of the matrix A, and this is also equal to the square root of the largest eigenvalue of A transpose A. So we will learn how to compute these quantities later on. So this is how your matrix norms look like. So you have here a unit ball. When you multiply it by your um, when you take the matrix norm for L2 norm, it produces this result. So unit ball gets stretched in one direction and compressed in the other direction. We have this largest stretch that is your value for that matrix norm. And the same thing here. You have actually stretched the unit ball for the one norm, which is a diamond shape, into this figure here, and the largest stretched value is your value for that norm. The same idea for the infinity norm. Orthogonal vectors x and y are orthogonal if and only if their inner product is 0. So x is orthogonal to y means that the inner product of x and y is 0. So it's how you test orthogonality. You take the inner product. If it is 0, then this is true. So it says equivalence, meaning if this is true, then the other one is true. And also the other way. So if this is true, then the other statement is also true. Angle between vectors, the angle theta is computed according to this formula. Cosine theta is equal to x transpose y divided by the product of the norms of x and y. Orthogonal projection of y onto x. So the orthogonal projection is just, in this case, y transpose ux. Ux is the unit vector in the direction of x. Okay, this is now your magnitude, and you multiply that by the unit vector, and you come up with another vector. Distance between two vectors is familiar. So the distance between two vectors is just the norm of the difference between the two vectors. Cauchy-Schwarz inequality. So this inequality is useful and very frequently invoked in many branches of mathematics for proving theorems, deriving things, and for approximations. So do not confuse the Cauchy-Schwarz inequality with the triangle inequality, because the Cauchy-Schwarz involves the inner product, while the triangle inequality involves a sum. Matrices. So matrices are one of the most important mathematical objects used in practically all fields of science and engineering. So matrix is a system of m by n elements, real or complex numbers, functions, derivatives, vectors, arranged in n rows and n columns. So the elements, as defined here, may be complex numbers, functions, and so on, but let's simplify and just think of these elements as real numbers. When m is equal to n, we have a square matrix. When m is not equal to n, we have a rectangular matrix. There are two types of rectangular matrix. The tall or skinny matrix, that's the case when m is greater than n, which means it's the rows there are more rows than columns. For the case when there are more columns than rows, we have a short or fat matrix. Matrices are used to represent systems of equation like this, and we write this more compactly using the notation AX equals B. We have the following definition for the linear transformation. Let V be a vector space and W be another vector space. V is n-dimensional while W is m-dimensional. And let T be a function with domain V and range in W, range W. That means, well, we have this notation, okay? T is the transformation that maps from your domain into your range. So T is a linear transformation provided that the two conditions are satisfied. The additivity condition and the homogeneity condition. So matrix A, an m by n dimensional matrix, is a linear transformation from Rn to Rm. Okay, so here m and n are the same, they're both equal to 2. This is how it looks like. So you have two vectors x1. When you multiply that by A, the linear transformation A becomes AX, and it looks like this. And when you multiply x2 by A, it becomes like this. So that's a linear transformation. The matrix may be viewed as a linear transformation that rotates, scales, and shears its input. So this is your input. When you multiply that by your matrix, which is a linear transformation, the output becomes like this. So it's scaled, multiplied along certain directions. So along certain direction, in this direction, it's multiplied by this much, and it's also multiplied by that much, is less than 1. And also it's rotated and sheared. Now we will go into the details of this transformation towards the end of this lecture. So the most common interpretation of a matrix is the row view. So this is the view that we have learned since high school days. We've been looking at matrices this way. So in this interpretation, the rows of the matrix A are seen as coefficients that are multiplied with the elements of the vector x. So this by that gives this element the second row multiplied by this elements of the vector gives us the second entry, the second element of your B vector, and so on. And this gives rise to a system of equations where we want to solve for the unknown elements of x. So geometrically, the solution is the point where two lines, in this case, defined by each equation intersect. So you have two lines intersecting, and the point of intersection, that is your solution. So we know that from high school days. So for this two-dimensional example, we have lines, but in general, in n dimensions, we have hyperplanes. So that was the row view, but now, since we're no longer in high school, we need to look at matrices differently. We need to look at matrices as columns, okay? So we have to look at, a matrix as composed of many columns like this, okay? this is the better way of looking at a matrix. In this view, the system of equations with n unknown x's, m unknown x's, is interpreted as a linear combination of the columns of the matrix. Okay, so this is your first column, second column. These are actually vectors. Look at them as vectors. And then now, these values here, x1, x2, and so on, are what? Are just multiplied to each of these vectors. So you can look at this entire thing as just a linear combination. So the system of equations with n unknowns is now interpreted as a linear combination of the columns of the matrix. And let's have an example. So this is the example. So here we have this vector 2, 1 and minus 1, 3. So you have two vectors. What values of x1 and x2 will give me this answer, this vector? So that's basically what this is saying. Since we're looking at this as a linear combination. So if we vary x1 and x2, if we allow x1 to vary from minus infinity to positive infinity, and the same with x2, it's clear that we can actually generate the entire two-dimensional space, right? So these two vectors can reconstruct R2 since they are linearly independent. However, if they are linearly dependent, what happens? We only reconstruct a line, not the entire two-dimensional plane. Okay, you have a line only, right? You have a line. So that line is a subspace in R2. Null space. The null space of A, denoted N, or null, of A is the subset of the vector space V, consisting of those vectors that A maps to 0. So this we define the null space. So the null space of A is the set of vectors orthogonal to the rows of A. So we will see why this is the case later on. Okay. When the null space is 0, which means that the only way for this to be true is x is equal to 0. That is the so-called trivial solution. Okay, that means that the columns of A are independent. And it also means that the determinant of A transpose A is not equal to 0. It also means many other things, but we'll talk about that later on. The determinant is a scalar that is uniquely associated with a square matrix with the following recursive definition. So this is something that's very familiar. We've done this also perhaps in high school, but I'm sure you've done this in college, so we'll not elaborate on this too much. So the properties of the determinant are the following. The determinant of A is the same as the determinant of A transpose. The determinant of a product AB is the determinant of A times the determinant of B. And very important, if the determinant of A is 0, that means that A is not invertible. meaning you cannot invert it. Okay, we'll talk about inverse matrix inverse later. So this is an if and only if statement. A is invertible. If A is invertible, then the determinant of the inverse of A is just the reciprocal of the determinant of A. So we know how to compute the determinant for a 3 by 3 matrix. So we compute this using the Laplace expansion or cofactor expansion that we have learned in our algebra course. So this procedure is general, but it becomes very inefficient when we have larger matrices. So later on, we will learn matrix decomposition methods that will give us a determinant for much larger matrices with little effort compared to this Laplace expansion technique. So this expansion uses the cofactor and minor. So the minor is this. Okay. See, the minor is an n by 1, n minus 1 by n minus 1 matrix that results from deleting the ith row, in this case I equals 1, and the jth column. So there are 3 minors here, and the cofactor is this product here and so on. So we know how to do this. The geometric interpretation of the determinant is the following. If we look at the vector again as composed of columns, column v1, v2, and v3, and this vector v1 is this vector here, v2, this second vector, and v3 is third vector. The determinant is just the volume of this parallelepiped. The parallelepiped generated by the columns of the matrix. Take note, however, that the value of the determinant can be negative. So let's just ignore the sign. So it becomes negative when one of this is pointing in the negative direction. So, but still you have a volume. So just ignore the sign, and it still gives you the concept of volume, the more familiar concept. Inverse of a matrix. So a square matrix is called invertible or non-singular if there exists a matrix B, also square, such that the product results in an identity matrix. P is called the inverse of A and is denoted by A inverse. A is invertible, means that the determinant of A is not equal to 0, and that's also equivalent to saying that AX is equal to 0 if and only if X is equal to 0. In other words, we have a trivial solution here. The only way for this to be true is the case when X is equal to 0. Okay? So that is it. That if this is true, then the determinant of A is not equal to 0, and also A is invertible, and also, of course, the matrix exists. Sorry, matrix inverse exists. So if this is not true, then the inverse of the matrix of that matrix does not exist. Okay. And the solution of the system AX equals B is X equals A inverse B. So now, what happens if this is not satisfied? Okay, you have a null space that's not just 0. We have a singular matrix. It is a square matrix that does not have a matrix inverse. Matrix is singular if and only if its determinant is 0. So it violates this condition. Inverse of a rectangular matrix. So if A is a rectangular matrix of dimensions m by n, and A transpose A is invertible, the solution of the system of equation is x equals A transpose A inverse A transpose times B. So this quantity here is the pseudo inverse, the Moore-Penrose pseudo inverse. Trace of a matrix. For a square matrix, the trace is the sum of its main diagonal elements. So the trace of A is just A11 plus A22 up to A and N. Here are some properties of the trace, which will be useful later on, perhaps. So the last property is the commonly used trick in many derivations. Okay, so the cyclical property of the trace of ABC. So the order of multiplication of the matrices must be observed. So it must be circularly permuted in the right way. So A is first here. You put it after C, make it the last. Okay, here the BCA, and that's now the same as the previous one, and so on. So you put the first, the last place. You have this equation. Rank of a matrix. For a matrix A, the number R of linearly independent column vectors is equal to the number of linearly independent row vectors. The number R is called the rank of the matrix, written this way. So some properties of rank. The rank of a matrix, an M by N matrix, is always less than or equal to the minimum, the lower of the two values. So if you have a 3 by 2 matrix, okay, that matrix cannot have a rank of 3. Okay, it can have a rank of 2 and also 1, of course. And for the square matrix, if the for the square matrix, the n by n square matrix, if the rank is n, then we know that the determinant is not 0. This means that the inverse exists, and so on. However, if the rank is less than n, then we have the case where the matrix cannot be inverted. So it's not invertible, it's a singular matrix. And it's also the case that the determinant is 0. Symmetric matrix, a square matrix A is symmetric if it is equal to its transpose. Orthogonal matrix, square matrix is an orthogonal matrix if its transpose is also its inverse. Okay. Some properties of orthogonal matrices. The transpose and inverse of an orthogonal matrix are also orthogonal. And the products of orthogonal matrices are also orthogonal. And the determinant of an orthogonal matrix A is either 1 or -1. Orthogonal vectors. Orthogonal vectors are unit vectors that are pairwise orthogonal. That means that their dot products are 0. orthonormal matrix. An orthonormal matrix is a square matrix with real entries whose columns and rows are orthonormal vectors. So this is an example of an orthonormal matrix. So if you multiply that by its transpose, you come up with a orthonormal, the identity matrix. Orthonormal basis. An orthonormal basis of B is an orthonormal set of vectors that spans B. Okay, so the question that we're asking here is that how do we find the orthonormal basis from an orthonormal set that spans the vector space B? And many of you already know the answer, but anyway, this is a review of the basic concepts in linear algebra, so bear with me. So the procedure is called Gram-Schmidt orthogonalization. So in GSO, we are given a set of vectors v1 up to vn that is a basis of your vector space B. We construct an orthogonal basis of V, and that orthogonal basis is your set of vectors W1, W2 up to Wn. And the procedure is as follows. We set W1 to V1, then we equate W2 to V2, okay, V2 here, and subtract from V2 the inner product of V2 and W1 divided by the inner product of W1 by itself and multiply that by W1. So this numerator and denominator are both scalars. Okay, so you repeat this and we come up with a set of vectors W1 up to Wn. But you need to normalize each of these. So you're not yet done. So the orthonormal basis U1 up to Un is formed by normalizing each Wi. So these should be normalized in this manner. So the procedure is the following. You have the following example here. So let's find the orthonormal basis for the following vectors. We have three vectors here, v1, v2, v3, and they have the following values for their elements. Let's now compute the basis. First step is to equate W1 with V1. You're done here. W2 is just using this formula equal to V2. Okay, it's V2 minus this quantity here divided by that quantity here, there, multiplied by V1, which is this. W1 now. Sorry, W1, which is the same as V1, and it's this quantity here, this vector here. And if you do the multiplication, this cancels out. This becomes 0. Similarly for W3. So the reason why this is 0 is because this vector is actually already orthogonal to the first one. So this is already orthogonal, but of course not normalized, no? So, and then we follow this formula and we come up with this this result. Again, these two quantities are 0, so we are very lucky because this vector is actually orthogonal to both this and the first one. So we're just lucky. but in most cases we are not lucky, so the computation becomes more complicated. But the procedure is the same. Okay, so of course in the exam I will not give you something like this, no. So if that's the case, the denominators can become very complicated, very confusing. So it's error prone. So after we have computed this, W1, W2, and W3, we normalize and we come up with this. We get this result. The unit vectors U1 is equal to this, U2 is equal to that, and U3 is equal to this. So the answer to uh, this question, what is the orthonormal basis for the following vectors, is simply uh, those vectors U1, U2, and U3. So from the very start, the three vectors were already orthogonal. Okay, because we were lucky, and because this was my example, no? So uh, I gave an easy example. Now it's just a matter of normalizing each of these, and you have now an orthonormal um, basis. Okay, so I'm sure you can do something similar. Now let's define the PSD, positive semi-definite matrix. A real semi-symmetric matrix A is positive definite if for any vector z is not equal to 0, z transpose A z is greater than 0. Okay, so that's the definition of positive definite. For positive semi-definite, the condition is this condition here, greater than or equal. And we denote this by this this um, symbol, the succeed symbol, or greater than symbol, or greater than or equal symbol. So if A is positive definite, its diagonal elements are positive, and each diagonal entry is greater than the sum of the absolute values of all the other entries in the corresponding row and column. Also, if A is positive semi-definite, then Z transpose A Z is equal to 0 is equivalent or implies that A Z is equal to 0 and vice versa. A Z equals 0 implies that Z transpose A Z is equal to 0. Okay. If A is non-singular, well, rather, A is non-singular if and only if it is positive definite. And finally, if A is positive semi-definite but not positive definite, then it is the singular. Positive semi-definite ordering. The positive semi-definite condition can be used to define a partial ordering on all symmetric matrices. This is called the Launer ordering or the positive semi-definite ordering. For any two symmetric matrices A and B, we write A greater than or equal to B if A minus B is greater than or equal to 0. So that's how we define this ordering. Let A and B be positive semi-definite matrices, and let A and B be non-negative scalars. Then A plus B is positive semi-definite. Okay. Now, why is this important? Now, what's the big deal about positive semi-definite matrices? Positive semi-definite matrices are important for determining convexity. So later on, when we discuss optimization, we will have to look at the convexity of functions. Um, and convexity um, is related to the Hessian being positive definite for a strictly convex function. And also, positive semi-definite matrices are important for determining the existence of the global minimum of a function. So if you're trying to optimize a function, minimize a function, you want to get the global minimum. And how do you know that you have actually arrived, or that your function has a global minimum? Well, you look at this. You look at the uh, positive semi-definite condition. Okay. Gram matrix. Suppose we have a collection of samples. We're now talking about data. And we define a matrix in this way. Okay. So the matrix, the gram matrix, which is n by n, is just the data matrix transpose x. Okay, data matrix x transpose x. So you have here the elements are the inner products x1, 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 x2, and so on. Gram matrices are positive semi-definite matrices. So this is an important result. We will take advantage of this result when discussing algorithms such as support vector machines and so on. Support vector machine is for CS280. We will not cover it in 284, but it's also important for other algorithms. Let's now talk about matrix spaces. Given a matrix A, an m by n matrix A, we have the following spaces. We have the column space, which is the span of the columns of A. So you have A having columns, and you take the span of those vectors, those column vectors. That is your column space. Then we also have the row space, which is the span of the rows of A. Now the range of A is just the set of y's such that y is equal to ax for some x in Rn. That is, of course, the definition of your range. Now, the null space is one of those spaces associated with A, and every vector in the null space is orthogonal to the rows of A. A very important uh, result. Every vector in the null space is orthogonal to the rows of A. Another result is that the null space and the row space of a matrix are orthogonal. So we will actually see why these two are correct. No? So later, okay. When A for the for A for the n by n matrix A is the square matrix A, the rank of A plus the dimension of your null space is equal to n. Okay. Again, for an n by n matrix A, you have the following formula. The rank of A plus the dimension of the null space of A is equal to n. So when the dimension of the null space of A is 0, we say that A is full rank. and A is therefore invertible. Eigenvalues of a matrix. Okay, so eigenvalues are extremely important in many areas, especially in engineering. We talk about eigenvalues of the system. So your circuit will oscillate if certain uh, conditions are satisfied, and these conditions are usually best understood when you use eigenvectors and eigenvalues. So, and in machine learning, we also use eigenvectors and eigenvalues for many algorithms. Um, or you can also use these concepts to analyze the behavior of your optimization process. So while you're training your neural network, for example, um, if certain eigenvalues satisfy certain conditions, then the optimization process will proceed as desired. Okay, so definition of eigenvectors and eigenvalues. The eigenvector U of an n by n matrix A is a non-trivial solution of the equation A U equals lambda U. And okay, so there's a missing U here. Okay, so it should be AU minus lambda U determinant. Okay, so this implies that the determinant must be 0 for a particular lambda called the associated eigen value. So eigenvalues are solutions to the characteristic polynomial determinant of A um, minus lambda I equals 0. Yeah, I think this is correct. Okay. If your n by n matrix is real, valid, and symmetric, then all eigenvalues lambda 1 up to lambda n are real. Also, we can find n eigenvectors u1 up to un such that the eigenvectors are mutually orthogonal to each other. That means that their product is 0, and each of these eigenvectors are actually unit vectors. And as a result, these eigenvectors now constitute a new basis for Rn. Now let's go back to the notion of positive definiteness. So how do we know whether your matrix is positive definite, positive semi-definite, and so on? By looking at the eigenvalues. A square symmetric matrix is said to be positive definite if its eigenvalues are all positive. For the case where you want to check whether it's positive semi-definite, you just have to check whether the eigenvalues are non-negative. So now, by just looking at the eigenvalues, you now know whether your matrix is positive definite or positive semi-definite. Why is that? Let M be any possibly non-square matrix, and we set A equals M transpose M. Then A is positive semi-definite since we can write Z transpose A. Z equals Z M transpose M, which is A, Z. And then we rewrite this as follows. Okay. So Z transpose M transpose is MZ transpose MZ. Okay. So this is just the inner product of mz by itself. And since we know that the inner product is always non-negative, then for any vector z, then we know that we have shown rather that your matrix is positive semi-definite. If we take M to be the matrix whose columns are the vectors xi for I equals 1 to n, then the A is the gram matrix of the set x1 to xn, showing that gram matrices are always positive semi-definite. Also, gram matrices are positive definite if the set S is linearly independent. Eigendecomposition. What is eigendecomposition? Eigendecomposition is a factorization. Okay, you factorize the matrix. Okay, it's a factorization of a matrix into its canonical form. What is canonical form? What does it mean? It simply means standard form. No, so the mathematicians, they like giving names to simple things. So standard form lang yan, so they call it canonical form. Okay, basically it means standard form. No? So again, the eigencomposition is a factorization of a matrix into its canonical form, where the matrix is expressed in terms of its eigenvalues here and eigenvectors here. Now let's take the square of the matrix. If we square the matrix A, it's basically P lambda P transpose squared. So that's this. And since P transpose P is equal to the identity matrix, so it's equal to 1, we just have P sigma squared P transpose. So in general, A raised to the n is P lambda to the n P transpose. So if you have a matrix and you want to raise it to the nth power, then you just raise all these quantities to the nth power, and that's it. You already have an answer right away. So you don't have to actually multiply the matrix by itself many, many times. Let lambda be an n by n real symmetric matrix that is positive semi-definite. And let P be an n by n real matrix. Then the n by n P transpose lambda P is real symmetric and positive semi-definite. Okay, so why do we have to compute the eigendecomposition of a matrix? Well, because again, it makes life easier for us. Well, the computation of the trace is very simple, really, no? But, we can also compute the trace of a matrix by taking the sum of its eigenvalues, okay? So the trace of A is just simply the sum of its eigenvalues. And more generally, the trace of A raised to the k is the sum of the eigenvalues raised to the kth power. How about the determinant? It's very complicated to get the determinant of a matrix, right? Very complicated now. So if you have a matrix that's 10 by 10, try doing that by hand and you'll go crazy. Okay? But if you're going to use eigenvalues, you can very easily compute the determinant of that matrix. It is simply the product of the eigenvalues of the matrix. So that's why we do eigendecomposition. We want to compute the trace, the determinant, the rank, The rank of a matrix is equal to the number of its non-zero eigenvalues. Okay. How are the eigenvalues of A and its inverse related? So they are related in this manner. Okay. So if lambda is a non-zero eigenvalue of A, then 1 over lambda is an eigenvalue of A inverse with the same eigenvector. So that's how these eigenvalues of A and A inverse are related. They're reciprocals of each other. Now let's talk about the spectral decomposition. Let's talk about the spectral decomposition theorem. Let A be an n by n matrix, and given orthonormal eigenvectors q1, q2 up to qn with associated eigenvalues lambda 1, lambda 2 up to lambda n, then AX is simply this expansion. Okay. Now let's have a look at an example. Okay, so you have suppose you have A equals this matrix here, and X equals 1, 1, 1. Okay. So if you compute the eigenvalues, we get these values here. Lambda 1 equals 1, lambda 2 equals 1, and lambda 3 equals 2. So we don't know yet how to compute the eigen values, but we'll get into that later on. But suppose we already know the values of the lambdas, and eigenvectors are these quantities here. Would like to see what happens when you multiply X with A. What is the transformation? Okay, so according to the spectral decomposition theorem, we have this expansion. So your lambda 1 is 1, lambda 2 is 1, and lambda 3 is 2. Now, Q transpose X gives us a value of 1 here. Q transpose X also gives us a value of 1. Q transpose Q3 transpose X gives us a value of 1 as well. So now what we have is this. Okay, lambda 1 times Q1, lambda 2 times Q2 plus lambda 3 times Q3. So what is the lesson that we have learned here? We're basically multiplying the vector by its lambda 3 in the direction of the coordinate axis. Okay, so it's important to understand this. So what is it? What does the eigenvalue signify? It basically stretches your vector in a particular direction by that amount. Do you get that? Again, you have a vector 1, 1, 1, and the eigenvalues are 1, 1, and 2. This means that if you multiply A by X, you get a stretching in this direction. Okay, so you don't stretch this. It still is 1. This still becomes 1, but this becomes 2. Okay, so eigenvectors or eigenvalues rather stretch the vector, the input vector, in certain directions. Okay, so this is stretched, this is doubled in size in this direction. Okay, so clear? I hope that's clear. So we have learned that eigenvalues are scaling factors. The eigenvalues actually scale, okay, they scale the vectors. Now, what happens if an eigenvalue is negative? When an eigenvalue is negative, as in this case, it's multiplied by -1, right? If it is multiplied by -1, it points in the negative direction. So basically, there is a rotation, right? There's a rotation, okay? So a negative eigenvalue means rotation. What if the eigenvalue is 0? If one of the eigenvalues is 0, then we have an injection instead of a bijection. So what is an injection? It's the following. Okay, the mapping x to y here is injective or one-to-one if for all x and y in x and ax equals ay implies that x equals y. That's what is meant by injective. And this means that the elements of the codomain are mapped to by at most one element of the domain. That is what is meant by injection. Okay, so if one of the eigenvalues is 0, that means we have this case. If all the eigenvalues are non-zero, then we have bijection. Bijection is this case. Bijection means one-to-one and onto. So a mapping is bijective or one-to-one and onto if for all x, y in x here, and ax equals ay implies that x equals y, and for all y in the codomain, there exists an x such that y is equal to ax. So that is what is meant by one-to-one and onto. This basically means that every element of the codomain is mapped to by exactly one element of the domain. So that's bijection. So again, when you have zero eigenvalue, okay, you have an injection. You have this case. And when you have a non-zero eigenvalue, you have a bijection. Spectral norm. So the spectral norm is defined in terms of a symmetric n by n matrix A. Let A be a symmetric n by n matrix with eigenvalues lambda 1 to lambda n. The spectral norm of A, denoted this way, is just the maximum of the absolute value um, of the lambdas, of the eigenvalues. So we take the absolute values of each of these and pick the one with the largest value. Okay, we now come to the most important part of today's lecture. Okay, that is the singular value decomposition theorem. In deep learning, it is the basis of important algorithms such as PCA or principal component analysis, which is in turn used for face recognition, analyzing genes to detect cancer, and many others. So the SVD theorem is the following. Any real valued m by n matrix can be written as A equals U sigma transpose, sorry, A equals U sigma V transpose, where U and V are orthogonal matrices with rank equal to the rank of A. So U and V are orthogonal matrices. They are square matrices whose columns form an orthonormal basis. So these are square matrices, m by n and n by n. Again, they form an orthonormal basis. Sigma is a diagonal matrix, not necessarily a square, containing the singular values which are all non-negative. Okay, these are all greater than or equal to 0. Um, and for I greater than R is your rank, the singular value is 0. So the columns of U are called okay, these columns here are called the left singular vectors, while the columns of V are the right singular vectors. So these columns here are the orthonormal eigenvectors of A transpose, while the columns of V, okay, are the orthonormal eigenvectors of A transpose A. Okay, so the vectors here have special names. Vi, these V's are called the right or input singular vectors of A transpose A, while Ui, U1, U2 up to UR are the left or output singular vectors of A transpose. Let's take a look at the quantity A transpose A. So this is your gram matrix. So if you do the math, if you do this calculation, A transpose A is just U sigma transpose times U sigma V transpose. And this becomes an identity matrix, so that now we have V sigma squared V transpose. This tells us that the V i's are the eigenvectors of A transpose A corresponding to the non-zero eigenvalues. If you remember our previous um, slide on this, okay, so the eigenvectors of this matrix here will be this. The eigenvectors are the columns of V. So sigma I will just be the square root of the eigenvalues of A transpose A. That's the case when I is less than or equal to the rank. Now, when I is greater than R, the rank of the matrix, the singular values become zero. And similarly, for A transpose, we have U sigma U transpose. And this time, the UIs are the eigenvectors of A transpose corresponding to the non-zero eigenvalues. Okay, and singular value um, is equal to zero when I is greater than the rank R. It's equal to the square root of the eigenvalue of A transpose. Matrix properties via SVD. So before we learned how to, we learned what matrix norms are. We know what the determinant is, but we have defined most of them in terms of a square matrix. Now, for the general case where we have a rectangular matrix, how do we get these norms? How do we get the determinant? Well, so these are computed very easily using the singular value decomposition. So for a general matrix of dimensions m by n, let R be the smaller of m and n. Rather, let R be less than or equal to the smaller of the two. And let R be the number of non-zero singular values of A. The rank of A is R, which is the number of non-zero singular values, as said earlier. Now, the L2 norm, the L2 matrix norm is just equal to sigma 1. What is the L2 matrix norm? It's the spectral norm. So the spectral norm is just equal to this. The Frobenius norm is equal to the square root of the sum of the squares of the singular values, the R singular values. The non-zero singular values of A are the square roots of the non-zero singular eigenvalues of A transpose A or A transpose. When A is equal to A transpose, then the singular values of A are the absolute values of the eigenvalues of A. If A is a square matrix, then as before, the determinant of A, the absolute value of the determinant of A is just equal to the product of the singular values. So this is wrong. This should be R. Finally, A is the sum of R rank 1 matrices as described by this formula. Let's analyze the action of matrix A on an input X. Suppose we have an input X. That input X is rotated, scaled, and rotated again by these three matrices. So X is multiplied by V transpose. Okay, so you have a an X here. You have a unit ball. When that unit ball is multiplied by V transpose, okay, it's V transpose X, you have this rotation of this unit ball, and it's still a unit ball, okay, but rotated. However, when you multiply this unit ball by sigma, you're actually scaling each of the coordinates of this unit ball. It's stretched in this direction because the corresponding singular value is larger than 1, so this becomes longer, stretched this way, and the singular value sigma 1 is less than 1, so it's actually compression. So the resulting object now is this ellipse. So this after the application of V transpose and sigma. Now you apply U to that, okay, to this result, which is this result. You rotate that. You rotate, so there's another rotation here. So now what you have is basically a rotation, okay? So the action of A on X is stretching and rotation of the unit ball. Okay, so that is well, the visualization of the SVD. So of course we just have here a two-dimensional matrix, 2 by 2 matrix, but in general you can extend the same idea to multiple dimensions, to n dimensions. And if A is not square or not full rank, there will be a null space. Okay, there will be a null space on your V or your U, and as a result, some dimensions will be annihilated. Okay, we'll see that in a short while, but just keep that in mind. That when your A is not square or not full rank, there will be some dimensions that will disappear, that will be annihilated. Okay, so let's now compute the SVD of a matrix. You're given this matrix here, and let's compute the A transpose. So very simple. So just rearrange this in this manner. Okay, so you know how to do the A transpose. Then we calculate U in the following manner. We take the A transpose, and the A transpose is this 2 by 2 matrix here. Then we compute the eigenvalues by setting this equation. Ax equals lambda x. Okay, so this is your A. This is now your new A rather. This is a new A times x equals lambda x1, x2. And then from here, you come up with a small system of equations and solve for, get the determinant rather of this system. and set the determinant to 0. So this diagonal times this diagonal is set to 0. So 11 minus lambda times 11 minus lambda minus 1 times 1 is equal to 0. And this gives us, okay, after doing this, factoring this properly, you have lambda equals 12 and 10. So we now know the two eigen values of this matrix A. Question: are the eigenvalues of A transpose A, not this one, this is A transpose, are the eigenvalues of A transpose A the same as that of A transpose? The answer is, for the non-zero eigenvalues, they should be the same. Okay, so we plug back into the original equations our result for lambda equals 10. We just put in 10 there, and we choose x1 equals 1 and x equals minus 1. So now we have this eigenvector that corresponds to the eigenvalue equal to 1. Then for lambda equals 12, we choose these two. X1 equals 1, x equals 1, and the eigenvector, this eigenvector now corresponds to the eigenvalue lambda equals 12. So these two eigenvectors now is your U matrix. Well, not yet. No, we need to do a Gram-Schmidt orthogonalization to make that a U matrix. You know how to do the GSO, right? Okay, we studied that earlier. So this is a simple operation because this is a 2 by 2 matrix. Okay, so now you have your U, which is normalized. Now let's calculate V. You know, we have already computed U. Let's now calculate V. For U, we need to get A transpose. For V, we need to get the Gram matrix, which is A transpose A. So let's compute that. A transpose A will, of course, be a 3 by 3 matrix. Okay. Now we repeat the same thing as before, as the one for U, and we come up with this result. Lambda is equal to 0 and 10 and 12. So you'll notice that 10 and 12 are the same values that we obtained earlier. It should be the case, no? As I've said, the eigenvalues for the previous calculation should be the same except for the zeros, no? So this one actually has an extra one, which is 0, because this is a 3 by 3 matrix, while the other one, U, is just a 2 by 2 matrix. Doing the same procedure as before, okay, where we set x1, x2, and x3 to some values, we get this. And applying the GSO process, okay, we get this matrix here. Okay, so if you're observant, okay, these are actually the same values that we obtained earlier. Our example, our GSO example is actually this, no? So remember this: 1, 2, 1, 2 minus 1, 0, 1, 2 minus 5. That's this. Right? 1 to 1, 2 minus 1, 0, 1, 2 minus 5. And our result is this. Okay? So these are the three vectors that now constitute your V matrix in our SVD example. Yeah, okay, so these are the very same values that we got earlier in our GSO example. So now, of course, we need to transpose this. So we compute sigma. Sigma is just the square root of 12 and the square root of 10. Okay, so these are our lambdas. You take the square root of these values, that would be your sigma. Putting them all together, we have the following. This is our original matrix. So this original matrix can be decomposed using SVD into three matrices. This 2 by 2 U matrix, this 2 by 3 sigma matrix, and this matrix here, which is the transpose of the V that we have computed earlier. So don't forget to do the transposition, otherwise you'll get your wrong answer for this matrix. Okay, so the SVD of a non-square matrix. So what we had earlier was what? A short and fat matrix. We have a 2 by 3 matrix. Okay, so this is a 2 by 3 matrix, and therefore we have a short or fat matrix. If you have a short or fat matrix, the decomposition will be the following. So the sigma will have columns that are 0. Okay. Okay, so this is your sigma. It has, in this case, a column that is 0. And it is on the right side of the matrix. Okay, as shown here in gray. Again, for the short and fat matrix, the lower rows of the V transpose matrix here will be annihilated by the zeros in the columns of sigma. Let's go back. So this is your column. Okay, this dimension here will be annihilated because of this, right? So this by that will give you a 0 here, and so on. Okay, so so this part here will be annihilated. Remember, we are transposing here. That's why we are looking at the rows this time instead of the columns. Okay, similarly for the tall or skinny matrix, the singular value decomposition will produce a sigma matrix that will have zeros in the lower row shown here in gray. But the one that is affected is not this, but the U matrix. So the left singular matrix U will have columns shaded here in gray that are annihilated when multiplied by the corresponding row in the sigma matrix, because these rows are 0. We will we can actually simplify this by getting rid of these gray areas. I will do that later. But in the meantime, let's compare SVD with eigen decomposition. So for eigen decomposition, most square matrices have an eigen decomposition. When I say most, I say most, which means not all. Okay, some square matrices do not even have an eigen decomposition. While for SVD, all as in all rectangular matrices have a singular value decomposition. So obviously, SVD is better because eigen decomposition cannot even deal with all square matrices. And there's that extra condition na kailangan square, that the matrix has to be square. But for SVD, it's general. It's a rectangular matrix, including square matrices, because squares are rectangles as well. When a valid eigen decomposition is available, we only have one set of eigenvectors for eigen decomposition. Okay, so which makes it easier. So that's the nice thing about having an eigen decomposition. You only deal with one. You only deal with one set of eigenvectors. On the other hand, for SVD, you have your left and right singular vectors. So you have two sets of orthonormal vectors or orthogonal matrices. But yeah, that's the price that you have to pay for being able to deal with the rectangular matrices. For eigen decomposition, in general, the basis is not orthonormal. Okay? The basis is not orthonormal for eigen decomposition. That's for the general case. However, for SVD, the bases are always orthonormal. Let's talk about the four fundamental subspaces. There are four fundamental subspaces associated with matrix A. A being an n by n matrix. You have the column space, which consists of all the combinations, the linear combinations of the columns of A, and the null space of A, which is the solution or the set of solutions for AX equals 0, and the row space of A transpose. The row space of A. The row space of A is the column space of A transpose, obviously. That is the linear combination of the row vectors of A that form a subspace of Rn. Okay, it is the same as the column space of A, as I said earlier. And finally, we have the left null space, which is the solution set Y for A transpose Y equals 0. So these are the four fundamental subspaces for a general matrix, a general rectangular matrix A. Now let's examine further the SVD. Okay, let's go back. We said earlier that these gray areas here are really not needed because they annihilate the vectors here, the dimensions corresponding to these vectors here. Okay, so we can actually make a more compact SVD by just getting rid of all these. So we do that and we call that the reduced SVD. So just take a look at the SVD of a non-square matrix, which has this reduced SVD. Again, the singular value decomposition of an n by n matrix whose rank is R will produce the following: a U matrix whose vectors, singular vectors, your left singular vectors are U1, U2, UR, up to UR, UR plus 1 up to UM. Okay, we have actually partitioned this matrix into two. The first singular or left singular vectors are these, and the remaining ones are these. And we call this first R vectors as UL, L for left, U left. And this part here will be your UR. So this U here would be composed of this partitioned matrix whose submatrices are UL and UR. And similarly for V, you have this right singular vectors V1 up to VR, VR plus 1 up to Vn, and we also partition this matrix into a V left and a VR submatrices. Now the sigma matrix is also partitioned according to whether they contain zeros, all zeros. Okay, so this part here are all zeros, so that would be partitioned, and this top left TL. Okay, the top left part is called sigma TL. That would be your submatrix. That would be an R by R matrix whose values are all zeros except for the diagonal, which are the singular values of your matrix A. So now we have this decomposition. Okay, U is UL and UR, V is VL and VR. Don't forget the transpose here. And when you transpose this, the rows become the columns become rows. So be careful with that. And then of course you have your sigma TL here, the top left submatrix of your sigma matrix, and all these are zeros. So now you can actually just simplify this into the reduced SVD U left, sigma top left, and V left transpose. So this is now your reduced SVD. So we have actually made the decomposition more compact by getting rid of the unneeded columns of U, sigma, and V. So you have now the reduced SVD, U left sigma, top left, V left transpose. Now the four fundamental spaces can be obtained from this reduced SVD. The column space of A is U left, okay? That forms the orthonormal base, an orthonormal basis here. And it is a subspace of R to the M with a dimension R, okay? So the column space, okay, UL is R dimensional. And the null space corresponds to the VR, okay? This part here, VR. These column vectors here define the null space, and it is a subspace of R to the N with a dimension N minus R because there are N minus R column vectors here. The row space of A is just VL residing in Rn having dimension R. And finally, the left subspace corresponds to UR, which is a subspace of R to the M having dimension M minus R. Now we come to the last slide of this lecture. Actually, the second to the last slide. So the last slide is just your references. So we come now to the fundamental theorem of linear algebra, so which is the following. For any matrix, for any n by n matrix, the column and row spaces of A have dimensions R, which is equal to the rank of A. Okay. The null space has dimension n minus R, and the left null space has dimension m minus R. So, okay. So here's your column space, dimension R. The null space has dimension n minus R here. The null space and the row space are orthogonal, and the left null space and the column space are also orthogonal. Okay, so that is illustrated by this, this perpendicular symbol here. So the column space, okay, the column space and the left null space are perpendicular to each other, or orthogonal, while the row space and the null space are orthogonal. So that is the fundamental theorem of linear algebra. References: the book of Gilbert Strand, Introduction to Linear Algebra, written in 1998. And also this book by Triefethen and Bao, Numerical Linear Algebra. Okay, with that, I end this lecture.